All right, so I'm going to keep this pretty quick so that our first speaker can get started. But to set the stage a little bit, I'll say just a few words on some recent trends in machine learning and deep learning and how those might impact robotics in the near future. And then we'll start with the main program of the day. So I'm going to cover kind of three themes that have kind of gained a lot of prominence in the last couple of years, and that we'll also see echoed in some of the talks today in deep learning and machine learning, but that also I think will impact robotics in a big way. And those are deep reinforcement learning, large data sets, and learning to learn or meta learning. So reinforcement learning is a particular class of methods very closely related to optimal control that deals with a very simple and very broadly applicable problem formulation where you have a robot, it chooses actions to interact with the environment, and the environment produces in response to those actions the next state and a reward signal. And the job of the robot is to take the actions that will maximize its long-term sum of rewards. So this is very similar to the optimal control framework. It's sort of the machine learning take on optimal control. And the only thing that the word deep in front of the term reinforcement learning means is that the mechanism by which the robot chooses the action to take is determined by a large high-capacity model, like a deep neural network. And the reason that this is significant rather than being just a footnote is that by using a large high-capacity model, it turns out that you can actually subsume a lot of the more complex kind of systems engineering that has been the dominant way of programming robots for decades. So for example, you can subsume state estimation inside this deep neural network. You can say that, well, it's just going to take in raw sensory observations like images, and it's going to directly produce actions as a consequence of that. So then you might not need an explicit state estimator. You might subsume some complex motion planning by having a really elaborate nonlinear strategy. So even though it's a simple tweak to the standard well-known reinforcement learning or optimal control framework, it turns out to be quite promising and potentially very impactful. So deep reinforcement learning has actually been around for some time. This is not by any means the earliest citation to it, but actually maybe the earliest that sort of is in the modern incarnation of this framework. This is from Sacha Lang and Martin Riedmiller, where they actually did deep reinforcement learning on a real-world system. Some of you might not be familiar with this work, where they had a slot car racing task. Many of you might be familiar with some subsequent work. This is from DeepMind, before it was Google DeepMind, for playing Atari games with Q-learning. And then, of course, there was work here at Berkeley on deep reinforcement learning for robots at Carnegie Mellon and many other universities. So at this point, actually, these techniques are being deployed much more widely. And, you know, contrary to what's kind of popular belief, perhaps, they are actually being used on real physical hardware. And although there are some very serious challenges there, this stuff is actually happening. So we'll hear more about deep reinforcement learning today. Large data sets. So the thing about deep networks, of course, is that they, you know, even though they can represent really complex functions, process raw sensory input, and so on, they typically require large amounts of data to succeed. And this should not at all be surprising from kind of a machine learning perspective. When you have a large high-capacity model, you have less bias, which means that you can fit your data better, but you have more variance, which means that you need more data if you want to avoid overfitting. So in kind of more traditional passive perception domains like computer vision, speech recognition, typically this kind of thing is tackled by simply producing more data, getting humans to label more images if you're doing image recognition, getting humans to annotate more audio if you're doing speech recognition. So what about robots? Well, there's this sort of conventional belief that robotics is the domain of small data sets, because generating data for a robot means actually running a robot. Something could go wrong, somebody, you know, could get hurt. You need to be careful, so you use small amounts of data. And I think what we've seen in the last few years that is very exciting when it comes to deep learning and robotics is that, in fact, people are starting to recognize that this might not actually be the case after all, that robots might actually be quite compatible with large data sets, and there's a very natural reason for it, which is that robots can collect their data autonomously. So in some ways, it's a machine that automatically produces data. You don't even need a human labeler for it. So we've seen a number of works that look at collecting large data sets using real physical robots, using multiple physical robots, as well as large data sets for training and simulation, like large data sets of shapes that can then be used for things like grasping. So we'll hear a little bit more about this later on today as well. And then the last topic, which I think is going to come up in a couple of talks this afternoon, involves learning to learn. So this is also related to the large data set question. You can say that, well, okay, if it's fine that you can run a robot for a long time and produce lots of data, but perhaps there are some tasks where you really do want to be able to learn quickly. Maybe if someone buys a household robot, it goes into their home, they want to show it how to do a new chore, you don't want it to have to collect, you know, millions and millions of images. So perhaps what you can do instead, if you want to retain the benefits of large high-capacity models like deep neural networks, is you can use your large set of prior data not to learn the particular task you want, but instead to learn how to learn. So this is an illustration actually from a paper by Oriol Vinyals and collaborators that illustrates learning to learn for an image classification task. Here the setup is that during training, you're not training how to classify images into specific classes. Instead, you're meta-training by giving little data sets that are labeled with particular class labels, and then from those little data sets, you generalize to little test sets. And by seeing lots of little data sets and learning how to generalize to little test sets, at meta-test time, you can then get a new data set with new classes you haven't seen before, and from that small data set, use what you've learned before about learning to generalize to a new test set. So this is in an image recognition setting, but later on in the afternoon, we'll see how this can be applied in robotics context, both a reinforcement learning context and imitation learning context.